All right, let's get right into it. Have you ever seen a machine learning model that looks absolutely brilliant on paper, just completely bomb in the real world? It's a super common story, right? A model gets a perfect score on its training data, but then it completely fails its first real test. Why that happens is what we're going to break down today, and trust me, it's fascinating. It really all boils down to this one single question. How can a model that seems to have learned everything perfectly still get it so wrong? Well, the answer is in the subtle but crucial difference between just memorizing facts and actually understanding a concept. You see, the problem starts when a model is, believe it or not, too good at its job. It can learn so incredibly well that it just goes way too far, picking up on all these tiny little details that it really should have ignored. Let's take a look at this in action. So imagine we're building a model to predict house prices based on their size. Our first attempt might be a simple straight line, just like this one. And you can see, it's not great. It kind of gets the general direction, but it's completely missing the real curve in the data. This is what we call underfitting. The model is just too simple, and its strong, kind of stubborn assumptions give it what's known as high bias. Okay, so now let's try a more sophisticated model. And that's much better. See this smooth curve? It captures the general trend pretty well, and it feels like it would actually make good predictions on new houses. This is our goal. This is a good fit. But here's the thing. The quest for perfection can be a real trap. What happens if we push the model to be even more accurate? And this is where it gets weird. Look at this thing. I mean, technically, it's a masterpiece. It hits every single data point perfectly. But can you see the problem here? This line is so complex and so wiggly, it hasn't just learned the pattern, it's literally memorized all the random noise in our data. This is overfitting, and it is a huge, huge problem. So let's go ahead and formally introduce the villain of our story today, overfitting. It's this strange paradox where a model's drive for perfection on the data it knows actually leads to its own downfall when it faces something new. So the textbook definition is that overfitting is when a model learns the training data too well. It's not just learning the signal, it's also memorizing all the random noise and all the tiny little flukes. And what that means is, while it might be a star student on the data it's already seen, it completely falls apart the second it encounters something new. And this really lays out the two extremes perfectly. On one side, you've got underfitting, or high bias, where the model's just too simple and it fails everywhere. And on the other side, you've got overfitting or high variance, where the model's way too complex, a genius on its homework but totally useless on the final exam. Our goal is to find that perfect sweet spot right in the middle. It's called the bias-variance tradeoff. So, how do we fight this villain? How do we combat overfitting? Well, there are a few common strategies people try first. Let's think of them as the first responders on the scene. The first line of defense is often, just get more data. The hope is that you can drown out the noise with more examples. Another tactic is something called feature selection, which is basically being pickier about the information you even let the model see. But the third, and often the most elegant and powerful approach, is a technique called regularization. But see, those first two approaches have some real-world limits. Getting more data? That's often super expensive or sometimes just flat out impossible. And with feature selection, where you're manually kicking out some of your inputs, you're always running the risk of throwing away something that was actually important. There's gotta be a better way, right? And there is. This is where we bring in the hero of our story, regularization. It's an incredibly clever idea that solves the overfitting problem not with brute force, but with an elegant appeal to simplicity. Here's the core idea behind it. Instead of just throwing features away, regularization just reduces their influence. You see, in a model, every feature has a weight that kind of determines how important it is. Regularization works by penalizing large weights, basically telling the model, hey, you can use all the features, but I want you to build the simplest possible explanation you can from them. So think of the model's learning process like a balancing act. Don't worry about the math here, just focus on the concept. On one side of the scale, you have the model's error. How well it fits the data. But now on the other side, we're adding a new item, a penalty for being too complex. This penalty can take different forms, like L2 or ridge, which penalizes the square of the weights, or L1, which you might know as lasso. So let's just translate that into plain English. The model is now trying to minimize this total cost. It's basically being pulled in two different directions at once. It's being pulled towards the data, trying to reduce its error,
But it's also being pulled back by this penalty, which keeps it from getting too complicated. It's this constant tug of war that forces the model to find a balanced, stable solution that can actually generalize to new data.
Okay, so how do we actually control this balancing act? Well, we have a tool for that, and you can think of it like a knob that we can turn to dial in just the right amount of simplicity. And that knob is a special parameter called lambda, represented by that Greek letter lambda. When we set the value of lambda, we're basically telling the algorithm how much it should care about that complexity penalty. So a small lambda tells the model, hey, focus on fitting the data. A large lambda says, nope, focus on being as simple as possible. So what happens when we go to the extremes with this knob? Well, look on the left. If we turn lambda all the way down to 0, that means regularization is completely off, and boom, we're right back to our crazy overfit villain. But now look at the right. If we crank that knob way too high, the penalty for complexity gets so huge that the model becomes super simplistic and we end up underfitting. The magic is all about finding that perfect balance right in the middle. Okay, so we've met the villain, we've met the hero. Now let's see the final outcome. What actually happens when we apply just the right amount of regularization to that overfit model we saw earlier? And there it is. Look at that. By adding that penalty for complexity, our wild overfit model has been tamed. It's now this smooth, sensible curve that does a great job of capturing the real trend without getting distracted by all the noise. This is a model that's ready for the real world. So let's wrap this all up with the key takeaways. Regularization works by adding a penalty for complexity into the mix. This encourages the model to shrink the influence of the less important features, which forces it to focus on what really truly matters. And that prevents it from just memorizing noise and creates a simpler, more robust model that actually works on new data. It's a really powerful idea. And that leaves us with a final thought to chew on. In machine learning, we've just seen that deliberately adding a penalty for complexity, intentionally making things simpler, can actually lead to a smarter, more effective result. So the question is this: if complexity is just a knob that we can turn, what's the next great problem out there that we can solve just by choosing to be simple?